You propose that space-based solar power can give humanity free, unlimited energy. If that promise is realized, what happens? The high frontier, Gerard O'Neill. Yes, it's part 3 of our space-based solar power exploration. And today we're going to ask what happens if space-based solar power delivers on that promise. What does abundance mean to the space industry, to civilization, to humanity? And are we close to building the high frontier? Today's guest is a very, very special guest. Is John Bucknell. He's the CEO and founder of Virtus Solis. He has at least 46 patents to his name, and he was, check this out, senior propulsion engineer for the Raptor full flow stage combustion Methalox rocket at SpaceX. And if that wasn't cool enough, he's the designer of a nuclear thermal turbo rocket.
Good morning. Great to be here.
Talk us through what you think of one versus the other. Hey, is Mars the play? Is O'Neill's cylinders the play?
To get all the way to Mars and have enough infrastructure that humans can live and work there, it's non-trivial, right? I mean, just getting there is hard. I mean, getting off the planet has been hard, and then getting to another planet is dramatically harder. And then what do you do once you get there, right? What's the driver? Who's going to finance all that? And I think that's really the gap. Once we start looking at what the high frontier says on the technologically feasible versus economically viable part, is like, how do you get enough people to work in the same direction to get you to the point of interest? And I think Mars and off Earth in general both require huge amounts of infrastructure to work, to make these economies work. And who is going to go there and make it work such that they can leverage all the capabilities of off-Earth resources and energy? Who is that going to be? Well, right now we really have only a couple of candidates, right? Less than one hand. And is there enough resources in the cislunar space to make it worthwhile? And the O'Neill vision, I think that's easier to get there, frankly. The whole mining the moon and working for Elon for a long time, he was like, yeah, there's no point doing that. We need to go all the way to Mars. And then in the last few weeks, he's like, no, we're going to go mine the moon and build computation in orbit. So even he can be convinced that maybe near term we should be doing local stuff before we go far away.
Why, back when you were working for SpaceX, Elon was so adamant that Mars was the solution, not O'Neill's vision of orbitals? And
the argument that Musk and all the Martian team, the Team Martian has had, is that, look, we need a biosphere ultimately that will support human life. You need a gravity well, a significant gravity well for human development. And we know that there's detriments to microgravity on the human physiology, and that we don't know how to fix that yet. Maybe, biology, technology is moving fast enough that maybe we'll solve that sooner than we think. But that's the argument for Mars, is like, look, it's still close enough to the sun. It has decent illumination. It's got resources that you don't have to go off planet to find. There's water there, and there's enough minerals to support a civilization, and it's far enough away that any thing that takes down this local civilization might find it hard to spread that disaster to somewhere else. Those are the arguments for Mars, ultimately, that it is far enough away that it's safe, but also far enough away that it's hard to develop. Those are the two counterpoints, right? And can you do something similar on the moon and cislunar space? Probably. We don't yet have the ability to go out and harvest near Earth objects, but there are several businesses stood up to do that, and having the ability to access those resources that it would be very expensive to do on the planet, I absolutely believe they're worth doing. So I think probably both is going to happen. Now, where in time that occurs are completely unsupported, because the vision for Mars is we're just going to build the most efficient transport possible, build everything here and just ship it, and then instant civilization. I think it's going to be a little bit more complicated than that, but who knows?
So back to the high frontier, back to O'Neill's model, it required a catalyst. And I had kind of an epiphany. All we're hearing today in the tech world is, AI this, AI that, and, oh my gosh, we're running out of power. And, how do we power these data centers? Are we at a moment right now where what's happening on the AI data center side, is that enough noise to create some momentum for space-based solar power? And if so, what could that look like?
I think the answer is yes, indirectly. And I struggle a bit with the whole, hey, the permitting, which is the permitting grid connection, are the real barriers to the build out of the compute terrestrially that you need. And the other big thing is to do it in orbit. We can't just take a rack that NVIDIA builds and put it in orbit. It just is not designed for that yet. And there's a couple of businesses that are stood up saying, yeah, we can adapt it. But having all this energy just go into compute, and if you put it in orbit and you're only using the solar energy for compute, what about the rest of us, right? I mean, one of the arguments I make for building out space solar is that those of us who live in the West, we all consume across all forms of energy somewhere in the neighborhood of 9 or 10 kilowatts. Some of us are a lot more, but the global average is like 1.8 kilowatts. And there's about 1 billion people, between 3/4 and 1 billion, that are at zero. So what are we missing out on development of humanity's capabilities by constraining people's resources, right? What does it look like when you unconstrain them? And if you put compute in orbit, all you're solving is the compute part of what the resource needs of all of us are.
How does civilization change the incentive so that the world isn't obsessed with energy for data centers in space or otherwise, and for the 1 billion people who have zero access to any?
Yeah, absolutely. And that loops back around to what my business is all about, is trying to lower the floor enough that a lot more of the developed world can, or even the undeveloped world, can have access to the resources they need. And certainly you look across what does a civilization need, and energy underlies almost all of it, and getting those costs lower than where they are today. When energy was really inexpensive, and that was the 50s, 60s, and slightly into the 70s, global economic growth, global GDP was growing very quickly, and energy costs were like 2 to 3% of global GDP in that time frame, and now we're like 14%. And how do you reverse those trends? Well, you got to figure a way to break the lock that we have today on energy costs. The energy costs continue to go up because we're not able to reduce the underlying structural elements of the energy costs globally. Space solar can do that. That can unlock energy at costs dramatically lower than where we are today. And frankly, with the model that we've built, you can build an asset, it generates energy, and then once the asset's paid for, it's basically free. And then what do you do with free energy? That's the big picture kinds of things that the outcomes that we're super interested in, is what does civilization look like once the underlying resource is free, and then conceivably all the downstream stuff become closer to free.
Could you give us some numbers on what you're proposing your company can do in terms of generating energy? How much?
When NASA dug into what Jerry O'Neill was doing in the late 70s, they spent somewhere in the neighborhood of $60 million on studies, and they produced a lot of reports, I think on about 1,200 pages worth of reports. And my team luckily has read all of them. And they got told no by Congress for the $3 trillion of today's money they would need to build the first power plant in 2006, like a long time, 26 years after they started. But in that time frame, photovoltaics, PV, was 5% efficient. Microelectronics didn't exist, and the space shuttle still hadn't flown in that time frame. So launch costs were speculative. And the National Science Council actually wrote a analysis of why NASA's proposal to return to Apollo-level areas of funding to build space solar didn't work. They're like, look, the technology's not there yet. The economics just aren't working. However, probably 40 years from now, based on the trends we're looking at, they probably will be there. And in 2018, SpaceX's Falcon Heavy flew, and launch costs were where they needed to be. Moore's Law and microelectronics have made basically the cost of any electronics almost free. Those are revolutions, right, in manufacture. So launch costs, photovoltaic cost, automation costs, all have dropped dramatically. And that's the basis of what Solis is we're building space-based solar power plants, leveraging mass manufacturing, using electronics manufacturing infrastructure to build enough generation to serve all of humanity at price points around $30 or $40 a megawatt hour, which are 3 or 4 cents a kilowatt hour during the period when the plant's being financed. And then it drops to like 50 cents a megawatt hour, which is 0.005 cents a kilowatt hour after 20 years of finance.
I read a stat that basically the big tech companies are spending $200 billion on essentially power infrastructure, right? $200 billion on power infrastructure. And they do that. They're not just building one system. Largely, they're building two systems, right? So you're spending twice the amount you are to have the backup power. The reliability issue is largely solved. So is there a need for 2N infrastructure on the power side when this stuff actually works?
I mean, that's been our argument all along. I mean, one of the qualities that space solar can offer, and really it's the only one, you have what's called the energy trilemma, where energy wants to be clean, firm, and low cost. And no energy technology other than space solar does that. And when we say firm, it's an energy business terminology that describes reliability. And most energy technologies are at least 2 nines, 99% reliable, but data centers want 4 nines, which is less than an hour a year downtime. Space solar is probably 5 nines if you have all the qualities that are necessary. And when we talk about the architecture that Solis has developed, it's designed for 4 nines minimum, probably 5 nines, because we put the solar panels in space where they're more productive. We have redundant generation capability on orbit, and then we have a wireless power transfer technology that allows us to deliver energy from orbit to the ground, super reliable by using radio waves that go through weather and clouds with no loss. And that's really the underlying offer that these technologies have.
So this moves into the political realm where the wind farms are getting signed off on, and what's it going to take for the politicians to sign off on space-based solar power?
I would argue that these advances are all profit driven primarily. So whoever is selling offshore wind, they have a hammer and everything's a nail. So offshore wind's going to solve it, right? Well, offshore wind's a lot more reliable than onshore wind, which is why they do it. But the cost per unit is non-trivial, just because engineering for saltwater, all of us hate saltwater that engineer things, because saltwater eats all the structural metals that you want. And then even though it's more reliable, it's not 100% reliable. It's not even 1 9 reliable. It's a fraction of a 9. So what do you do about that? Well, you have this N+1 problem. Again, you need long distance energy transmission, which is cables. You need batteries to back up, or you need a thermal power plant, or you need all of them. And just because there's offshore wind available in the UK, and because it's infrastructure, terrestrial the land is owned by a lot of people, and getting around the eminent domain problem is the reason why transmission here in the United States and elsewhere is hard. You can't build cables to get the energy where you want it to where people are using it. So you sidestep it, and you put the assets in the water. So that is driving, I think the UK's average energy costs are about $350 a megawatt hour today. And that's not, I mean, that's bad. It drives deindustrialization when your energy costs are high. How do you solve that? Well, you find a solution that doesn't require huge amounts of capex and a low utilization rate.
The math issue is a little funky too, right? Because if you compare it with other technologies, other energy technologies, some get a ton of subsidies, some don't. Like, how do you balance the math that people throw at you related to, other technologies?
So we would argue that energy technologies have unit costs that are directly tied to the complexity, right? When you build a thermal power plant, it's a gas turbine. Thankfully, there's a lot of jet engines built out there. So we have the tooling to build that. But then there's this burner and all the other parts. So there's probably 20,000 unique parts in a thermal power plant. And you need to have manufacturing capacity for all of them to build at scale. And the same thing applies to space solar. And again, because my team, frankly, all of us came out of some sort of mass manufacturer background. And my co-founder and I both worked at General Motors a long time ago. And one of the interesting things about General Motors, it was vertically integrated, just like SpaceX is today for a very long time. And they had their own electronics manufacturing facility. They made all the radios, all the end controllers, every bit of electronics in the cars for a very long time. And in fact, they have a chip fab in Kokomo, Indiana, the only empty chip fab in North America, by the way. That they're manufacturing all their electronics, millions of devices per year for GM's entire manufacturing volume globally. And their costs to build all these complicated electronics were tens of dollars a piece. But because they're making so many of them, you can get those unit economics. And that's the same underlying complexity argument that we're making, is that we're making two devices, effectively, but millions of them.
When we first spoke, John, you wrote us an email. I was going to quote from your email because I think this connects to that. We were talking about the high frontier. And you said, obviously, a frontier means freedom from the old structures. You propose that space-based solar power can give humanity free, unlimited energy. If that promise is realized, what happens?
Yeah, the structures that we have, that humanity has built, right? So governments are one. We've had them for a very long time. They've taken lots of different forms. But what do governments do for you? Well, it's communal protection from a number of things, right? It establishes common, like language, for example, so you can talk to one another. And then there's other structures. We talk about banks, we talk about land rights, other things, and those are all basically they're defensible. They're something that you own and operate. And then we have this thing we call capitalism, which is a way to optimize constrained resources. And that's the key part of that. Is what capitalism does well is organizes flows such that the resources are maximally utilized, right? But what happens when resources are not constrained? And that's the post-capitalism discussion. And what does post-capitalism look like? It's not too many people agree what that looks like, but you can speculate, you can imagine. And this is the topic we were talking about earlier, is like a lot of us are inspired by science or speculative fiction. And lots of people are taking guesses at what that looks like. And I've read a few post-capitalist stories and other papers and what that might mean. But ultimately, by unconstraining resources, I think the Medici's structure doesn't work anymore, because everyone has access to the same resources that the top of the pile has, right? And that's really what unconstrained resources means.
So let's talk through this. So figure out space-based solar power. It gets implemented. Countries start going, hey, I'm putting up a receiver station here. I'd love to get some power from you, and then another country does that and another country does that. Talk us through the first couple of years of that iteration. What does that look like in your mind when people start procuring their own power?
A lot of technological challenges are solved with cheap energy. Like, for example, 80 to 85% of the world's energy needs across everything is fossil fuels. And a significant fraction of that is just petroleum, right? So how do you break that? Because there's only half a dozen sources globally of petroleum right now that satisfy most of the world's needs. So those are very constrained on who owns it, who controls it, and everything. You could synthesize any form of hydrocarbon, and all it takes is electricity and water and a little bit of carbon dioxide generally. And there's sources in the water and in the air. If you don't know this, the carbon dioxide that we have in the air is at equilibrium with the carbon dioxide in the water. And there's a lot more water than there is air on this planet. So anyone who has access to electricity, air, and water can make their own fuels. So you could say, hey, I'm going to break the chokehold that the Middle East has on us, or anywhere else, on availability of diesel fuel, which powers all our industrial equipment, all our farms, everything. So, past the use cases for electricity directly, which is the data centers and, powering your microwave oven and powering your home, heating your water. The next thing is make the fuel. The next thing after that is desalinate water, right? So if you have access to water, but it's not clean enough to irrigate your crops, cheap energy lets you take the salt out. And then you can irrigate basically anywhere there's water, regardless of whether it's salt water or not. So you've solved the basic energy, transport, because there's a lot of use cases for petroleum that don't electrify well. And as someone who's worked on batteries are complicated, and they're also resource constrained. There's minerals in there that are hard to get at. But you solve those two and solve the ability to make your own food. Man, you've solved a lot of the world's underlying challenges almost immediately.
Is there anything unlimited, abundant, free energy gives us that is detrimental to the future of humanity? Is there a yin to the yang of this? Is there a negative?
I mean, absolutely. I mean, this is part of the prior discussion around the limits of growth and exponential growth. And then, yeah, what happens when all your needs are met? Well, it seems like people do what they want. Lots of interest in art, for example, and entertainment. But there are those of us who would like to make things. So I don't know that there is any clear answer on what happens when humanity's basic needs are met.
So according to some, there are, say, 72,000 more things we can chuck up in low Earth orbit. Most recently, SpaceX made a decision to bring their constellation down, assuming some things that are going to be happening in the coming years that will affect maybe some collision avoidance. They do a lot of collision. These satellites have to do a lot of coordination to make sure they don't run into each other, right?
Yep.
Was it 800 maneuvers a day that you said, was it, that they were doing?
Say what you will about Elon. He's got all of our best interests in mind. His assets up there, in order to provide value, they need to know where things are, and they know. And then an automation of what we would normally call dumb matter is a big deal, right? These maneuvers are no big deal if you have what we call space domain awareness. And the Kessler Syndrome only is assuming everything's dumb. And things are going to run into each other, and collisions are going to create debris and more debris and more debris. And we're in the midst of a solar cycle. I mean, the sun's been very active, and this is right around the peak. This last year has been the peak. So the move by SpaceX to lower significant fraction of their assets into lower orbits improves the performance, number one. But number two, they're up high because our atmosphere has been inflated by the increased output of the sun, and they drag satellites down. I mean, so that altitude at which they get dragged down is going to continue to drop over the next 11-year cycle. The middle of the 11-year cycle is right around 2031 or so. So the minimum altitude you can operate a satellite is going to drop dramatically. And but operationally, space is still pretty huge. The total number of satellites in orbit is still dramatically lower than the number of aircraft, the commercial aircraft that are in the air at any given moment in time. Obviously, there's a limit to how much you can put up there, at least in the LEO orbits, but the higher orbits are basically empty. We intend to go to an orbit called Molniya, the only orbit with a name. It's Russian.
What's it called?
Molniya. It's Russian for lightning. It was a spy satellite orbit in the 60s, but it's if you want to put something up that's ground synchronous, which means it passes over the same spot in the ground, you're going to take the time it takes the Earth to rotate, which is called a sidereal day. It's 23 hours, 56 minutes, and divide that by the integer. So geostationary, geosynchronous, that's divide by 1. Molniya is a stable orbit, that's divide by 2. You keep going lower and lower, and you get more and more often the Earth's shadow, but you can do 4-hour orbit, 6-hour orbit, 3-hour orbit, all the way down to 90 minutes is the lowest you can fly without falling out of the sky. And all those orbits, like up there, Molniya's got like 5 things. It's basically empty.
Like if we were to think about it like a real estate perspective, right? It's like there are particular slots where Leo has more of a wide range where you could stuff stuff in. Is that accurate or no?
Leo has a number of shells, we would call them, altitudes you can operate at. So there are things that are going over the poles and around. We call those polar orbits, and some fraction of them are sun synchronous, which means they always fly over the terminator between day and night. There are ones that are equatorial, that are flying around the equator. There are ones that are inclined. So all those orbits basically all fly east to west, effectively. West to east, is because that's the way the Earth rotates. And as you go higher orbits, you could do more and more shells that have huge amounts of volume, and you're passing through it basically what's empty. So you go up to geostationary, there's not very much stuff up there because those are regulated slots. People pay for them to operate their telecom satellites, but nothing in geostationary has ever been hit by anything because it's so empty up there.
People pay to use them. Doesn't that imply someone owns them?
It's a agreement globally around spectrum usage. Government regulates it, says, okay, yes, you can have this slot. So there's a global coordination around geostationary. But the interesting thing is that the access to orbit costs have dropped so much that almost nobody cares about geo anymore because it's so cheap to get to LEO.
Who's orbit's landlord? Like who do we have to call to? Yeah,
it's interesting.
You have to know. Yeah.
Other than geo, it's the Wild West. No one owns anything. and this is the frontier thing again, there's almost no regulatory structure in outer space. Now you've got outer space treaties around, hey, am I going to put a weapon up there and other things. But once you're up there, you can do what you want.
So the dumb thing that you mentioned, the Kessler Syndrome with 7,200 or 72,000 pieces left to throw up there, those would be just on devices that aren't able to coordinate with other devices and say, hey, Mark, get out of my way. I'm coming around. Boop, boop. And we move stuff around, right? So we have more room in LEO than a lot of people are saying we do, but we're launching more stuff in there at a rate that's exponential than in the past, right?
The number of launches that we've had globally has been ever increasing, and the number of devices putting up are ever increasing. There are limits, right? But the interesting thing about LEO is that those orbits decay, and eventually these satellites run out of propellant, the ability to stay up there. So LEO will clean itself out relatively rapidly, like on the decadal time scale. Like we said, at the moment, we're at the solar maximum, but the solar minimum means you can put more stuff up at lower altitudes, but the next time the solar cycle comes along, those will get dragged down.
This solar cycle is fascinating that it changes the altitude of these orbits. Absolutely, it's blown my mind. I love it.
Yeah. And it's funny that the only reason we know about it is because people used to take their telescope and look at the sun and count sunspots. That's the only way we know how active the sun is counting sunspots. I mean, it's still today what we have. So, in fact, a lot of satellite developers didn't realize that this was a thing and designed their satellite at the solar minimum and then put it up there at the solar maximum, and then their satellite came right back down again. So space people are not fault free.
John, I've got to, as we're kind of landing the satellite here before it burns out. Let me ask you a fun question. If you could grab, the top 10 most influential people in the world, grab them by the collar and say, we're headed in this direction. Here are the 3 things we really need to do as a species.
As a species, right? I mean, you would argue the most influential people are generally the people that have a lot of resource, right? Either you're at the pinnacle of some government running and you have access to tax streams, or you're a businessman and you have access to revenue streams from your businesses. So the answer to the top 3 things, what should we solve? Obviously, basic human needs are one thing. And then what aspects of those are the biggest challenges, right? I mean, all of us are going to die from cancer eventually. Can you solve that? I don't know, but there's a lot of engineering on human biology and actually all the biology that's probably solvable. What does it look like when we don't have disease anymore, or what we categorize as disease? So I don't know if I answered your question, Jeremy, but those are the kinds of things I think about.
Oh, it's good. Well, what can we expect from you guys in the next couple of years? What goals do you have for your organization? What goals do you have for your technology and its application?
Yeah, unfortunately, we're very pragmatic engineers. So we have a number of milestones that we want to meet, but we hope to fly our first power plant in 2030. So that's not that long in the future. So building that first one and then showing it what it can do, and then having customers globally say, hey, this is something we want, and vote with their feet effectively. All right.
Sounds amazing.
And then the next step is like solving the next few problems that we're interested in. But if we can solve energy, that would be amazing.
That would be a good start. Yeah.
Yeah. Just a little problem. Just figure out energy. Yeah.
Solving energy. This has been awesome. Thank you, John. What did you say? Those who own the resources have the influence, and that's kind of lodged in my mind now, and it will be. And the culture of space will ultimately emerge from the politics of space, I fear, or hope, or not sure.
Hopefully we just don't bring the baggage from the old house to the new house, though, right?
Yeah, that is the paramount strategy, isn't it? I will just say for our listeners, we are in space season. We have a new book at Book Club, Space to Grow. This week we'll be learning about the Apollo missions, SpaceX in more detail, Blue Origin. So that's going to be fun. Later in the month, we have Philip Metzger coming on. We'll be speaking about rockets and the politics of space and some other. In fact, John, if you have any questions for him, that would be great. Audience, if you have any questions for a former NASA scientist, drop them in the comments. Let us know. Read The High Frontier, Jeremy's book recommendation for life. Like, subscribe wherever you're watching this, and we will see you next week. And in the meantime, be disruptive, stay curious.
Keep thinking on paper.